let's find the potential function of this vector field. So we're just going to assume that this vector field is already conservative. If your teacher gives you a question to tell you to find the potential function of a vector field, but it's not conservative, they're kind of evil. I don't know what to say. I'm not going to lie. But if you want to test this yourself, just find the curl of this vector field, and it should give you the zero vector identity, or just zero. You just I can write down zero vector identity like so. But to get this started, just so you know, this vector field, let's just assume it's conservative. We didn't test it out, but we're going to assume so. But when a vector field is conservative, it is the gradient of some function. Let's call it psi. Therefore, the first component is, when you're finding the gradient, remember the first component is the x partial. The second component of psi is the y partial, and the third component is the z partial of psi. So let's get that straight first. And if you find the integral of some derivative, right, some derivative, you just get the original function or some new function. So if I find the integral of this for your first component of your vector field with respect to x, you can find the function psi with some arbitrary constant or some functions that we are going to talk about later. So let's find the integral with respect to x so we can actually solve for psi here. So this is the x partial for psi, but if we solve for the integral with respect to x, we should get something that looks like psi. So the x integral, or the integral with respect to x of this function, is x squared yz plus x to the power of 3. Is that fair? Now here's the thing, whenever you find the integral of something, there's some constant. But in this case, there's partial derivatives. So we can say that there is a function that is dependent on y and z here. And the reason why is because when you derive with respect to x inside of this vector field, or inside of this first component of the vector field, you're going to get rid of any constants. So you're going to get rid of any functions that aren't reliant on x here, or any terms that aren't reliant on x. Let's say if you add another thing like y squared plus, I don't know, z squared, and you found the x partial of this new guy right here, these would just cancel out. So once you find the integral again, these aren't going to appear. These x squared plus z squareds aren't going to appear because they already disappeared once you found the x partial derivative. So therefore, there's probably some function that's going to be dependent on y or z. Sometimes it could be 0, but in this case, I think it was, in my notes it says it's not. So now that we have this, well, we could treat this as actually the potential function, except it's not actually fully complete. Let's actually make some space here. Let's change the color for that. Let's use red. So this is currently our psi function, but it's not complete because we haven't solved for g of y of z. So what can we do next? Well, if this is our psi function and this is equal to our y partial of psi, well, we can find the y partial of our psi function here. So if we find the y partial of this currently potential function here, you'll get x squared z plus, and since you're finding the y partial, x cubed is treated as a constant, so this just cancels out, plus our y partial of g. And if you were to find this, well, this is actually equal to our second component of our vector field. So 2y plus x squared z. And as you can see here, you can actually cancel out x squared z. And your y partial of g is actually equal to 2y. So this right here, the y partial of this function is equal to 2y. And hopefully you can guess what I'm going to be doing next. But I can find the integral with respect to y here. So I can just get g. All I want is just g of y of z. If you find the integral of this, you get x squared. So, I mean y squared, sorry. But remember, if you find some derivative with respect to y, you're going to cancel out whatever has any functions that aren't dependent on y. So just like some function like z squared, with no y multiplied by it. So you're going to have a new function. What's the next letter is h after z. So this will be your new g of y of z. So if you were to add all of that together into your original psi function, you would get, so let's write that here actually. You get x squared plus yz plus x cubed plus gy of z is equal to this guy right here. So you get y squared plus h of z. This is still your potential function. All we did was solve for g after calculating some integrals and derivatives, or partial derivatives, using the properties of a conservative vector field. Now that we have this potential psi function, again, we can find the z partial of this psi function now to find this last component right here. So the z partial of psi is equal to, of this guy psi right here, is equal to x squared y, x cubed and y squared cancels out because they are treated as constants, plus h, or the z partial of h. And this right here is equal to the z partial of your, or the third component of your vector field. So remember, this is our potential functions. We're just slowly increasing our knowledge of our potential function by finding derivatives and setting them equal to components of our vector field. So now that we have this, we can set this equal to our third component. So this guy right here, equal to our third component of our vector field, 4z cubed plus x squared y. And you can cancel out your x squared y's on both sides. You turn out to get, so z partial of h is 2z minus 4z cubed. And if you find the integral of this, 4z cubed, with respect to z, then you'd get z squared minus z to the power of 4. And this is equal to our h function. Because if you find the integral of some derivative of some function, you just get left off with the derivative of the original function, h in this case. So since this is our h function, we can actually include this into up here. And if we were to do that, we would get phi, let's put that here, phi is equal to x squared yz plus x cubed plus y squared plus z squared minus z to the power of 4. So besides some arbitrary constant that is impossible to find unless if you're given a point on this potential function, this is our answer for our potential function. Now that we found our potential function, psi, a good property, or a very convenient property of a conservative vector field, is that the gradient of psi is equal to your vector field. Let's leave that in the middle here. So let's go ahead and actually find the gradient of psi after we solved it and see if it's equal to our vector field here. So the gradient of psi is, the first component is the x partial of our psi function. So the x partial of this is like so, 3x squared, and the rest aren't dependent on x, so they are constants. Let's just get canceled out when you're finding the x partial. Now let's find the y partial. Well, the y partial is x squared z plus 2y. And the z partial of our psi function is just x squared y plus 2z minus 4z cubed. So if you compare this gradient that we just calculated with your vector field, you can see that everything is equal. So this is equal to this. What did I just do? This is equal to this if you just switched around the terms. And then this third component is equal to this if you, again, switched around the terms. Now I'm going to warn you guys, this next problem is kind of long, so be prepared. So remember, the properties of our conservative function here, we're just going to assume this is a conservative, which means the curl of our vector field is equal to the 0 vector identity. Nope, almost, I just erased the question. But this is our x partial of our potential function, psi. This second component is our y partial of our potential function. And the third component is z partial. Remember, it's just a gradient. Your vector field is just the gradient of your potential function. So keeping that in mind, we're going to find the x integral, or the integral with respect to x of the first component. Now you could do this in any order, but I just like to start at the beginning because it's more orderly. So we're going to find the x partial, or not the x partial, the integral with respect to x. And we get something that turns out like this. xyz squared plus 3x squared plus some function that is dependent on y or z. So remember, if you have the x partial of this, any terms that aren't dependent on x and are just dependent on y or z will get canceled out. So we will have some function that takes that into account, which is the g in this case. So let's find the, so this is our potential function so far, psi. Actually, let's set this equal to psi. So this is our current potential function, or some possible potential function. Its box is out so it doesn't get confused. And we're going to find the y partial of this. So we're going to find the y partial of our current potential function. And the y partial of this would just be x cubed cosine of y plus xz squared. X is treated as a constant, so this cancels out, plus the y partial of g. And the second component of your vector field is equal to the y partial of your potential function. So we can set this entire thing equal to the second component of our vector field. The second component is x cubed cosine of y minus 4 times y to the power of 3 cosine of z plus xz squared minus 1. Now, as you've noticed, you could probably cancel these out. Not probably, you can cancel these out. And you can cancel out these terms as well. And you're left off with something that looks like this. G, your y partial of g is equal to negative 4 times y cubed times cosine of z minus 1. Now, once you have this, you can find the integral of your g partial. And then you would get, with respect to y, and then you would get g, your g function's value. So let's find the integral of this. So the integral of this is integral of negative 4y cubed cosine of z minus 1 dy. is equal to negative y to the power 4 of cosine z minus y. And this is equal to our function g. Sorry, I have to add that we have to take into account the z partial as well. So this is equal to our g of y of z. So this guy can go up to here. We have a new potential function that we should take into account. Let's write down this new potential function. X cubed sine of y plus xyz squared plus 3x squared plus your new g value, or function of g, which is minus y to the power 4 cosine of z minus y plus some function that's dependent only on z. Now what do we do next? Well, we just do the same steps again. We're just slowly uncovering the clues for our potential function, and we just take the z partial again of what we have here. Let's box this in so that, yeah, I'm going to use the line tool, man. That's so much better. Okay. So we just take the z partial of this. So the z partial of this is equal to, well, this cancels out because it's not dependent on z. And the z partial of this term is 2xyz. This cancels out, not dependent on z, and this does not cancel out. Sorry, I wrote the x over it instinctively. This turns into plus y to the power 4 sine of z. And this cancels out because it's not dependent on z. And then we have our z partial of h. And we can set this to our third component of our vector field. So y to the power 4 sine of z plus 2xyz. And what do we get? Well, everything actually cancels out. So since everything cancels out, our function of h, so this function right here, is just equal to 0. So if the partial derivative is equal to 0, then the integral with respect to z of our partial function is also equal to 0. Therefore, h of z is equal to 0. So in the end, our potential function will be equal to x to the power of 3 sine of y plus xyz squared plus 3x squared minus y to the power 4 cosine of z minus y. Plus 0 technically if you add the n here. But this is our total potential function. And the gradient of phi here would be equal to the x partial of everything here. So the x partial of everything here is 3x squared sine of y plus yz squared plus 6x. And then the next component is the y partial. So the y partial of your potential function is x cubed cosine of y plus xz squared minus 4y cubed cosine of z minus 1, comma. And once again, I don't think I could fit this inside the. Oh shit. Wait, let me move this. Let's see if I can move this entire thing, because I'm running out of space right now. Okay, let's erase this 2. So this is z squared, and then let's move this down. Actually, let's make it smaller. Yeah, we'll have enough space. And then if you find the z partial of your potential function, you would get 2xyz minus y to the power of plus y to the power 4 sine of z. And this right here is equal to, you can check that for yourself, but this is equal to your vector field, maybe if you swapped around a few terms.